Welcome back to my video series on Scikit-learn for machine learning. In the previous video, we learned about k-fold cross-validation, a very popular model evaluation technique, and then applied it to 3 different types of problems. In this video, I'll be covering the following. How can k-fold cross-validation be used to search for an optimal tuning parameter? How can this process be made more efficient? How do you search for multiple tuning parameters at once? What do you do with those tuning parameters before making real predictions? And how can the computational expense of this process be reduced? Let's just briefly review the steps of k-fold cross-validation, as well as its benefits and drawbacks. First, we choose a number for k, often 10, and split the dataset into k partitions or folds of equal size. The model is trained on all of the folds except one, then tested on the remaining fold, and evaluated using the chosen evaluation metric. That process is repeated k-1 more times, such that each fold is the testing set once and the training set all other times. The average testing performance, also known as the cross-validated performance, is used as the estimate of the model's performance on out-of-sample data. That performance estimate is more reliable than the estimate provided by train-test split because cross-validation reduces the variance associated with a single trial of train-test split. And as we saw in the last video, cross-validation can be used for selecting tuning parameters, choosing between models, and selecting features. However, cross-validation can be computationally expensive, especially when the dataset is very large or the model is slow to train. Let's now review how we used the cross-val score function in the last video to select the best tuning parameters. It's important to understand this code because it will help you to understand the role of GridSearchCV, which I'll be covering in the next section of this video. In this case, we were trying to select the best value for k for the KNN model when predicting species on the iris dataset. We'll start by importing the relevant functions and classes, and then creating the feature matrix X and response vector Y. Next, we'll instantiate the k-neighbors classifier with a k value of 5, represented by the n-neighbors parameter. The model object, which we called KNN, is used as the first parameter in cross-val score. The other 4 parameters are the feature matrix X, the response vector Y, the number of cross-validation folds to use, and the evaluation metric of our choice. We're choosing to use 10-fold cross-validation with classification accuracy as the evaluation metric. Cross-val score returned 10 scores, namely the testing accuracy for each of the 10 folds used during cross-validation. Remember that cross-val score takes care of the entire cross-validation process, including splitting X and Y into the 10 folds, which is why we passed it the entirety of X and Y, and not X train and Y train. The scores object is a NumPy array, and so we can use its mean method in order to calculate the mean, which we use as the estimated accuracy for the k equals 5 model on the iris dataset. We want to repeat this process for a variety of k values to choose the k which will most likely generalize to out-of-sample data, and thus using a for loop is a natural choice. Pay close attention here because this is the code that we're going to replace with GridSearchCV. We start by creating two lists. K-range contains the integers 1 through 30 and indicates the values of k that we want to try, and k-scores is an empty list that will be used to store the cross-validated accuracy for each of the 30 iterations. The for loop iterates through k-range, and within the loop, we instantiate k-neighbors classifier with the chosen k-value, use cross-val score to perform tenfold cross-validation, and then append the mean of the 10 scores to the k-scores list. Finally, we'll print the 30 cross-validated scores. As you would expect, the fifth score in this list is 0.966, which we knew from above would be the cross-validated score when n neighbors equals 5. Finally, we plot the k values against the accuracy. We see that the values 13, 18, and 20 for k appear to be best. Even though the code above is not particularly difficult to write, you could imagine that this is something you might want to do very often, and thus it would be nice if there was a function that could automate this process for you. That is exactly why GridSearchCV was created. GridSearchCV allows you to define a set of parameters that you want to try with a given model, and it will automatically run cross-validation using each of those parameters, keeping track of the resulting scores. Essentially, it replaces the for loop above, as well as providing some additional functionality. To get started with GridSearchCV, we first import the class from sklearn.gridsearch. Exactly like above, we create a Python list called krange that specifies the k values that we would like to search. Next, we create what is known as a parameter grid. It's simply a Python dictionary in which the key is the parameter name, and the value is a list of values that should be searched for that parameter. As you can see, this dictionary has a single key value pair in which the key is the string n neighbors, and the value is a list of the numbers 1 through 30. Next, we'll instantiate the grid. You'll notice that it has the same parameters as cross-val score, except that it doesn't include x or y, but it does include paramGrid. You can think of the grid object as follows. It's an object that is ready to do tenfold cross-validation on a KNN model using classification accuracy as the evaluation metric. But in addition, it has been given this parameter grid so that it knows that it should repeat the tenfold cross-validation process 30 times, and each time the n neighbors parameter should be given a different value from the list. Hopefully this helps you to understand why the parameter grid is specified using key value pairs. we can't just give GridSearchCV a list of the numbers 1 through 30 because it won't know what to do with those numbers. Instead, we need to specify which model parameter, in this case n neighbors, should take on the values 1 through 30. One final note about instantiating the grid. If your computer and operating system support parallel processing, you can set the njobs parameter to -1 to instruct Scikit-learn to use all available processors. Finally, we fit the grid with data by just passing it the x and y objects. This step may take quite a while depending upon the model and the data and the number of parameters being searched. Remember that this is running 10-fold cross-validation 30 times, and thus the KNN model is being fit and predictions are being made 300 times. Now that grid search is done, let's take a look at the results, which are stored in the grid scores attribute. This is actually a list of 30 named tuples. The first tuple indicates that when the n neighbors parameter was set to 1, the mean cross-validated accuracy was 0.96, and the standard deviation of the accuracy scores was 0.05. While the mean is usually what we pay attention to, the standard deviation can be useful to keep in mind because if the standard deviation is high, that means that the cross-validated estimate of the accuracy might not be as reliable. Anyway, you can see that there is one tuple for each of the 30 trials of cross-validation. Next, I'll just show you how you can examine the individual tuples, just in case you need to do so in the future. I'm going to slice the list to select the first tuple using the bracket 0 notation. Because it's a named tuple, I can select its elements using dot notation. Parameters is simply a dictionary containing the parameters that were used. CV validation scores is an array of the 10 accuracy scores that were generated during 10-fold cross-validation using that parameter. And mean validation score is, of course, the mean of those 10 scores. It's easy to collect the mean scores across the 30 runs and plot them like we did above, so let's just quickly do that. We'll use a list comprehension to loop through grid.grid scores, pulling out only the mean score. And when we plot the results, we can see that the plot is identical to the one we generated above. Now you might be thinking that writing a list comprehension and then making a plot can't possibly be the most efficient way to view the results of the grid search. You're exactly right. Once a grid has been fit with data, it exposes 3 attributes that are quite useful. Best score is the single best score achieved across all of the parameters. Best params is a dictionary containing the parameters used to generate that score. And finally, best estimator is the actual model object fit with those best parameters, which conveniently shows you all of the default parameters for that model that you did not specify. As you might have noticed in the plot, there are two other values for k, which also produced a score of 0.98. I don't know for sure how GridSearch decided to choose k equals 13 as the best, but some limited testing indicates that it probably just picks the first parameter it tested that achieved that score. It might have occurred to you already that sometimes you'll want to search multiple different parameters simultaneously for the same model. For example, let's pretend you're using a decision tree classifier, which is a model we haven't yet covered in the series. Two important tuning parameters are max depth and min samples leaf. You could tune those parameters independently, meaning that you tried different values for max depth while leaving min samples leaf at its default value, and then you try different values for min samples leaf while leaving max depth at its default value. The problem with that approach is that the best model performance might be achieved when neither of those parameters are at their default values. Thus, you need to search those two parameters simultaneously, which is exactly what we're about to do with GridSearchCV. In the case of KNN, another parameter that might be worth tuning other than k is the weights parameter, which controls how the k nearest neighbors are weighted when making a prediction. The default option is uniform, which means that all points in the neighborhood are weighted equally, but another option is distance, which weights closer neighbors more heavily than further neighbors. Thus, I'm going to create a list of those options called weight options, in addition to the 30 integer options in k-range. Again, I create a parameter grid, and in this case, the dictionary has two key value pairs, one pair for each parameter to be searched. Now, I'll instantiate the grid and fit it with data just like before. This is known as exhaustive grid search because GridSearchCV is trying every possible combination of the nNeighbors parameter and the weights parameter. Because there are 30 options for nNeighbors and 2 options for weights, tenfold cross-validation is being performed 60 times. Let's take a quick look at the results. You can see that there is a tuple for every possible combination of nNeighbors and weights. Once again, we'll examine the best score and the best parameters. It turns out that the best score did not improve, and thus using nNeighbors equals 13 with the default value for weights is still the best set of parameters for this model. Next, I want to briefly remind you of what to do with these optimal tuning parameters once you've found them. Before you make predictions on out-of-sample data, it is critical that you train the model with the best known parameters using all of your data. As you can see, I instantiate KNeighbors classifier with the best parameters I found above, and then fit it with X and Y, not X-train and Y-train. In other words, even if you use train test split earlier in the model building process, you should train your model on X and Y before making predictions on new data. Otherwise, you will be throwing away potentially valuable data that your model can learn from. Here, I've just made an example prediction on a made-up data point. However, GridSearchCV gives you a shortcut to this process. By default, GridSearchCV will refit the model using the entire dataset and the best parameters it found. That fitted model is stored within the grid object, and it exposes a predict method to allow you to make predictions using the fitted model. In other words, the code in this cell accomplishes the same thing as the code in this cell. Obviously, this is only useful if you're running GridSearchCV right before making predictions, but it can be quite handy at times. Finally, let's take a look at Randomized Search Cv, which is a close cousin of GridSearchCV. The problem that Randomized Search Cv aims to solve is that when you're performing an exhaustive search of many different parameters at once, the search can quickly become computationally infeasible. For example, searching 10 different parameter values for each of 4 parameters will require 10,000 trials of cross-validation, which would equate to 100,000 model fits and 100,000 sets of predictions if tenfold cross-validation is being used. Randomized Search Cv solves this problem by searching only a random subset of the provided parameters and allowing you to explicitly control the number of different parameter combinations that are attempted. As such, you can effectively decide how long you want it to run for, depending on the computational time you have available. As with GridSearchCV, we import the Randomized Search Cv class from sklearn.gridsearch. With Randomized Search Cv, you specify parameter distributions rather than a parameter grid. For discrete parameters, meaning parameters for which you provide a list of discrete values, like integers or strings, this specification looks exactly the same as before. In this case, both of my parameters are discrete, and so paramdist is no different from paramgrid. However, if one of your tuning parameters is continuous, such as a regularization parameter for a regression problem, it's important to specify a continuous distribution rather than a list of possible values so that Randomized Search Cv can perform a more fine-grained search. I don't have an example to show you here, but some of the resources I'll mention below include examples of this. Anyway, we can now instantiate the randomized search, fit it with data, and take a look at the scores. You'll see that paramdist is used instead of paramgrid, and there are 2 new parameters, niter, which controls the number of random combinations it will try, and random state, which I've set for the purpose of reproducibility. From the grid scores, you can see that 10 random combinations of parameters were tried. And once again, we can look at the best score and the best parameters. We can see that even though it only tried 10 combinations of n neighbors and weights, it still managed to find a combination that has just as high a score as the combination found by GridSearchCV. It's certainly possible that Randomized Search Cv will not find as good a result as GridSearchCV, but you might be surprised how often it finds the best result, or something very close, in a fraction of the time that GridSearchCV would have taken. I've set up a quick experiment here in which I run RandomizedSearchCV with niter equals 10, and I repeat this process 20 times, recording the best score each time. As you can see, most of the time it does result in a score of 0.98, and when it doesn't find that score, it's still close to 0.98. In terms of practical recommendations, I would usually recommend starting with GridSearchCV, but then switching to RandomizedSearchCV if GridSearchCV is taking longer than the time you have available. When using RandomizedSearchCV, start with a very small value of niter, time how long that takes, and then do the math for how large you can set the niter parameter without exceeding the amount of time you have available. As always, the Scikit-learn documentation is helpful if you want to learn more. The first link is their user guide covering the topic of grid search in general, followed by links to the detailed documentation for GridSearchCV and RandomizedSearchCV. Next is a comparison of randomized search and grid search, also from the Scikit-learn documentation, which provides some code that demonstrates how much time a randomized search can save you over an exhaustive grid search. Next is a video segment in IPython Notebook on randomized search by Andreas Mueller, who is one of the core contributors to Scikit-learn. The relevant portion of the video, which I've linked to, is just 3 minutes long, but the rest of the video is worth watching if you want to learn about the more advanced features of Scikit-learn. The final resource is a paper by Yoshua Bengio, famous for his research on deep learning, which argues in favor of using a random search process for parameter tuning. As always, I appreciate you watching and look forward to your comments and questions. Please subscribe on YouTube if you'd like to be notified when my next video is released. Thanks again, and I'll see you soon.